Today I Anshu from BSc Chemistry and first year Organic Chemistry by Dr. J.M. Sehgal. Chapter Dienes. Introduction. The alkynes, or as they are more commonly known as the dienes, are unsaturated hydrocarbon containing two carbon-carbon double bond per molecule. They have the general formula CnH2n-2 and the isomeric with alkyne. But the behavior of dienes and alkynes is quite different from each other. Classification. Dienes are divided into three classes depending upon the arrangement of double bond in the molecule. The three classes are isolated dienes. The dienes in which double bonds are separated by more than one single bond are called isolated dienes. For example, 1,4-pentadiene. Cumulated diene. The diene in which two double bonds are present between successive carbon atoms are called cumulated dienes or alkenes or cumulines. For example, 1,2-propadiene or allene. Conjugated diene. The diene in which the double bonds are separated by a single bond are termed conjugated diene. For example, 1,3-butadiene. Nomenclature. Cumulated dienes are commonly named as alkyl derivative of allenes, which is the simplest member of these type of dienes. For example, methyl allene, CH2 double bond C double bond CH double bond CH3. IUPAC nomenclature of all type of diene is similar to that of alkene, except that the numeral di is added before the suffix "ene" to indicate the presence of two double bonds. For example, 1,2-propadiene, 1,2-butadiene. Relative stabilities of diene. It is interesting to note that difference in the relative location of double bond in their molecule cause appreciably difference in the relative stability of different classes of diene. The data on the heat of hydrogenation of alkene and dienes clearly show that conjugated dienes are not more stable than the non-conjugated one. For a diene, that total heat of hydrogenation may be expected to be the sum of heat of hydrogenation by individual double bond. This is found to be so far non-conjugated dienes. For instance, the observed heat of hydrogenation of 1,4-pentadiene is 254.4 kilojoule mole inverse, while the expected value is 251 kilojoule mole inverse. But in case of conjugated dienes, the observed value are lesser than the anticipated value. For example, the actual heat of hydrogenation of 1,3-butadiene is 238.2 kilojoule mole inverse, which is 12.8 kilojoule lesser than the expected value. Similarly, the heat of hydrogenation of 1,3-pentadiene is about 16.7 kilojoule lesser than the expected value. Now, two isomeric dienes which differ only in the relative location of double bond, example 1,4-pentadiene and 1,3-pentadiene, give rise to the same alkane on hydrogenation. Still, if the conjugated dienes evolves higher energy than non-conjugated alkane on hydrogenation, still if the conjugated dienes evolves lesser energy than non-conjugated one, only means that the former contains lesser energy than the later. In other words, conjugated diene system is more stable than non-conjugated diene system. The greater stability of conjugated dienes may be explained in terms of resonance or delocalization discussed in section 3.6. 3.5 Structure of 1,3-butadiene. It has been stated above that conjugated dienes are more stable than non-conjugated dienes. The extra stability of conjugated dienes can be explained in terms of their structure and as discussed below by considering the structure of 1,3-butadiene. 3.5.1 Resonance structure. Unlike non-conjugated dienes, conjugated dienes exist as resonance hybrid of various contributing structure. For instance, 1,3-butadiene is a resonance hybrid receiving contribution from many structures, the more important of which are. It should be noted that the structure of second and third involves separation of charged particle as such structure I, which does not involve any separation of charge, is the most stable and therefore the most important of all the contributing structure. The actual structure of 1,3-butadiene is a resonance hybrid which lies somewhere in between the contributing structure but resembles the structure of first more closely. This means that the bond between C1, C2 or C3 and C4 is not pure double bond but quite close to it. Similarly, the bond between C2 and C3 is between a single and double bond but nearly to a single bond. This is in keeping with the fact that bond length between C1 and C2 or C3 and C4 is nearly the same as that of C double bond C is 134 picometer, while the bond length between C2 and C3 is somewhat lesser than that of CC single bond. Thus, the relative greater stability of butadiene can be attributed to resonance. The resonance energy being 14.6 kilojoule mole inverse situation is responsible for the greater stability of other conjugated dienes as well. Orbital structure. The orbital picture of conjugated dienes affords a better way of understanding the nature of bonding in conjugated dienes. For this purpose, let us again consider 1,3-butadiene as a typical case. Each of 4 carbon of 1,3-butadiene uses 3 sp2 hybrid orbitals for the formation of sigma bond. For an unhybridized p orbital for the formation of pi bond. Shows p orbitals of 4 carbon atom of butadiene before the formation of pi bonds overlaps of p orbitals of carbon 1 with that of carbon 2 and of the p orbitals of carbon 3 and 4 in shown in figure 3.1b. However, if the 4 carbon and the hydrogen attached to them lie in the same plane, then the p orbitals of C1 and C2 can also overlap as depicted in figure 3.1c. This means that there is an overlap of p orbital at C1 with C2 and C2 with C3 and C3 with C4 as shown in figure 3.1d. This results in the formation of pi molecular orbital which covers all 4 the carbon atoms. Figure 3.2e as already explained. Such a molecular orbital which is spread over nuclei of more than 2 atoms is known as delocalized molecular orbital, and the electron present in it termed as delocalized electron. As in case of normal or localized molecular orbital, delocalized molecular orbitals also consist of 2 electron cloud, one lying above the plane of the atom and other lying below it. Figure 3.1e. The presence of delocalized orbital is supported by the fact that the bond length between any 2 adjacent carbon atom in 1,3-butadiene neither corresponds to carbon single bond length nor carbon double bond length. p orbitals of 4 carbon atom of 1,3-butadiene before the formation of pi bond. B. Overlap of p orbital of C1 with C2 and C3 with C4. Overlap of p orbitals of C2 and C3. Overlap of p orbitals of C1 with C2, C2 with C3 and C3 with C4. Delocalized pi molecular orbital of 1,3-butadiene. Thus, the greater stability of 1,3-butadiene is due to presence of delocalized electrons, as each pair of delocalized electrons attracts and is attracted by 4 and not 2 nuclei. The same explained also applies to other conjugated systems. More recently, it has been suggested that the greater stability of conjugated dienes is due to variation in bond length and bond energy due to particular hybrid state of carbon atom. Method of formation of dienes. Dienes are generally produced by the suitable variation of method employed for the preparation of simple alkene. The more commonly employed method are given below. First, catalytic dehydrogenation of alkane or alkenes. For example, 1,3-butadiene may be prepared by passing vapors of N-butane over heated chromium Cr2O3 Al2O3 catalyst. 1,3-butadiene is also obtained by passing vapor of 1-butene or 2-butene over heated nickel phosphate or calcium phosphate. Dehydrogenation of dihalogen derivative, for example, on heating with alcoholic potassium hydroxide 1,3-dichloro-3-methylbutane give isoprene. Dehydrogenation of diols in the presence of acid, for example, dehydration of 1,4-butane diol by heating in presence of sulfuric acid or phosphoric acid results in the formation of 1,3-butadiene CH2OH. CH2OH में H plus H heat minus 2H2O makes CH2 double bond CH double bond CH2. Pyrolysis of cycloalkene retrodiol Elder reaction, for example, 1,3-butadiene can be prepared by passing vapors of cyclohexene over heated nichrome and alloy nickel, chromium and iron. Chemical reactions of dienes are the chemical properties of dienes are essential due to presence of two carbon-carbon double bond in their molecule. Thus, two non-conjugated dienes behave in exact the same manner as simple alkenes, except the attacking reagent is consumed in twice the amount required for one double bond. In case of conjugated dienes, however, the property of double bonds are considerably modified due to characteristic relative arrangements of double bond. This relative arrangements enables the two double bonded to interact with each other so as to modify the behavior of the molecule as a whole. Thus, conjugated dienes are characterized by the greater stability and the occurrence of 1,4 addition reaction. The important reaction of dienes are discussed below to illustrate their behavior. Electrophilic addition reaction 1,2 and 1,4 addition reaction. Dienes undergoes the usual electrophilic addition reaction shown by alkenes. However, due to presence of double bond in the molecules of dienes, the total quantity of addendum is naturally 2 times that required for alkene. The important electrophilic addition reactions are given below. Addition of halogen. When treated with halogen, dienes react with 2 moles of halogen per mole of dienes to form tetrahalogen derivative. For example, 1,3-butadiene give 1,2,3,4 tetrabromobutane. The relative interesting point, however, in what happens when only 1 mole of addendum is made to react with 1 mole of diene. In such a case, that the two double bonds in non-conjugative dienes act independently of each other and addition take place across either of double bond. For example, 1,4-pentadiene makes 4,5-dibromo-1-pentene. But a different situation prevails in case of conjugated dienes. To illustrate it, let us consider the addition of 1 mole of bromine to 1,3-butadiene. The product obtained consists of mixture of 3,4-dibromo-1-butene and 1,4-dibromo-2-butene as shown below. The formation of 3,4-dibromo-1-butene is not surprising as it is the result of normal addition, also termed 1,2 addition, to adjacent carbon atoms linked by double bond, but formation of 1,4-dibromo-2-butene due to 1,4 addition appears to be unexpected. Mechanism of 1,2 and 1,4 addition of two conjugated dienes. To understand the occurrence of 1,2 and 1,4 addition reaction, let us examine the mechanism of addition of bromine to 1,3-butadiene. The reaction takes place in 2 steps through the initial formation of allylic carbocation. Formation of carbocation as the bromine molecule approaches the dienes and get polarized. The positive polarized bromine adds to C1 of the butadiene to form allylic carbocation A and negative bromide ion. A primary carbocation should also be formed by the initial addition of bromine to C2, but the ion A is formed in preference to the primary carbocation, as a former is not only a secondary but also an allylic cation which is stabilized by resonance between the structure A and B. The two contributing structure A and B differs from each other in location of double bond and of two positive charges. In the resonance hybrid of these structures, the positive charge is not localized on C2 and C4 but is spread over the both as shown below. Addition of bromide ion. It is clear that there are two positive charge center in the cation which may be attacked by negative bromide ion in the second step of addition. Addition of bromide ion at C2 would give 1,2-di addition product, while addition of bromide ion at C4 would give 1,4 addition product. Addition of halogen acid. Addition of halogen acid to conjugated dienes is similar to the addition of halogens. Addition of 1 mole of halogen acid to a conjugated dienes give rise to both 1,2 and 1,4 addition product. For example, 1,3-butadiene plus HCl make 1,2 addition product and 1,4 addition product. Mechanism to start the reaction. 1-butadiene molecule subtract hydrogen ion from hydrogen chloride to form a allylic carbocation and a negative chloride ion. Initial addition of hydrogen ion could also take place as C2, giving up a primary carbocation CH2 double bond CH2 positive, but the ion C is formed in preference to this primary carbocation, as the former is not only a secondary but also an allylic cation which is stabilized by resonance between structure C and D. The resonance of hybrid of these contributing structure may be represented as shown below. Thus, there are two positive centers which may be attacked by negative chloride ions in the second step of addition. Addition of chloride ion at C2 would give 3-chloro-1-butene, while addition at C4 would give 1-chloro-2-butene. Effect of temperature on 1, 2 and 1,4 addition to conjugated dienes. It has been found that the ratio in which the 1, 2 and 1,4 addition product are formed in a result of electrophilic addition to conjugated dienes is largely governed by temperature at which the reaction is carried out. Generally speaking, 1,2 addition product is formed preferentially at lower temperature, while 1,4 product is predominantly at higher temperature. Explanation of the effect of temperature on 1, 2 and 1,4 addition. The effect of temperature on 1, 2 and 1,4 addition reaction may be attributed to following reasons. E activation leading to 1, 2 addition product is less than that of leading to 1, 4 addition product. As such, 1, 2 addition take place more readily than 1, 4 addition. However, 1, 4 adduct once formed is more stable than 1, 2 adduct. Second, both the addition product can undergo ionization, forming a common carbocation. This leads to an equilibrium between the two product and the carbocation as shown below. It may be noted that the carbocation 1 is the same as the intermediate carbocation formed during the first step of addition, that is this. Since the energy difference between 1, 2 adduct and carbocation 1 is lesser than between 1, 4 adduct and the carbocation, ionization energy 1, 2 adduct take place readily while 1, 4 adduct take place slowly. At lower temperature, ionization of product occurs to a very small extent only, so that the 1, 2 adduct which is formed faster is the main product isolated. This means that at lower temperature, the relative amount of two products obtained are in accordance with their relative rates of formation. In other hand, the reaction is kinetically controlled. At higher temperature, ionization becomes more important. The 1, 2 adduct, which is thermodynamically less stable, readily ionizes, while 1, 4 adduct, although formed slowly, does not ionize readily. As such, the 1, 4 adduct is present in large quantity when the equilibrium is reached and therefore is the main product obtained. In other words, at high temperature, the reaction is thermodynamically controlled. Free radical addition reaction. Like simple alkenes, conjugated dienes also undergo certain free radical addition reaction in the presence of suitable organic peroxide. Moreover, addition of free radical can again lead to formation of both 1, 2 and 1, 4 addition product. For example, CH2 double bond CH में CH double bond CH2 plus Br CCl3 peroxide makes 1, 2 addition product and 1, 4 addition product. Mechanism. The mechanism of free radical addition such as given above summarized as follows. The resonance hybrid of E and F may be depicted as. It may be noted that the allyl free radical formed in step 3 in a resonance hybrid of structure E and F. In the resonance hybrid, the odd electron is distributed between C2 and C4. As a result, these allies free radical can form either 1, 2 or 1, 4 addition product. By abstracting a bromine atom from another molecule of Br CCl3, the newly formed CCl3 radical then carries on the chain process. It is interesting to note that free radical addition to conjugated dienes proceed at much faster rate than similar reaction with the simple alkenes, even though conjugated dienes are themselves more stable than simple alkene. This unexpected reactivity of conjugated dienes toward free radical addition attributes to much greater stability of intermediate allyl free radical as compared with the intermediate free radical formed with simple alkene. Therefore, the net reactivation for the formation of intermediate allyl free radical is lesser than E activation for the formation of intermediate free radical in case of simple alkene. As such, the free radicals addition to dienes take place more readily and at faster rate. Di-yield reaction 4 plus 2 cycloaddition. This is the one most important reaction of the conjugated dienes. It involves an addition reaction between a conjugated dienes and a compound containing a double bond called dienophiles. to form 6-member ring. Since the reaction involves addition of 4 pi electron system to pi electron system leads to the formation of cyclic product. It's often referred to as 4 plus 2 cycloaddition reaction. The product formed is often called Diels-Alder reaction. The simplest example of Diels-Alder reaction is between 1,3-butadiene and ethylene and dienophiles, but the reaction takes place very slowly and in low yield. The reaction take by the concerned single-step mechanism, during which C1 and C4 of the conjugated diene system gets attached to double-bonded carbon of the dienophiles. As the result, two new sigma bonds are formed at the low cost of 2 pi bonds of the dienes and dienophiles. As it's clear from the above example, Diels-Alder reaction take place very readily when substituted alkene containing electron withdrawing groups are used as a dienophiles. For example, the reaction between 1,3-butadiene and acrolein dienophiles take place 373 Kelvin to form adduct in